All right. So, focus. Focus. We're talking about values of extrema today, extreme values of a function. Extreme values in a function show up as the top of peaks and the bottom of valleys, high points and low points. Yeah, we sort them into two categories. The first are called local extremes, sometimes called relative extremes. The other type are called absolute extremes, also called global extremes or global extrema. So local and global, relative and absolute. You can mix and match. Your book mix and matches for some odd reason I don't understand. Your book is going to use relative and absolute and sometimes local and absolute. And it can't seem to make up its mind. So, yay. We're going to start with local or relative, and then we'll move to absolute. So the mathematical definition for a local minimum is that a function f has a local, we're starting with maximum, maximum at point B in an open interval a to c if the function at point B is lower than all of the other function values for every point in that region. A lot of function notation for saying that the point B is the lowest point in the area. Wait, highest. This is maximum, sorry. And I'm going to stick a word on top of that area, specifically the local area around B. It doesn't have to be the highest point in the entire graph. It just needs to be the highest point in the area around it. Meaning if here is B, both sides of B are coming down so that B is at the top of a hill. That's a relative extreme or a relative maximum. Any point in the graph that is at the top of a hill, even if that hill is not the highest hill in the picture. Yeah. That means if a graph has multiple peaks, goes back up and down, it's going to have multiple relative maximums. And that's okay. Yeah. Minimums work the same. Minimums are the lowest point in an area of your graph. They're the bottom of a valley. So we have a local minimum at point B, comma, f of B, when it is the lowest point in the local area. Just like with maxes, if I have multiple valleys because my function's going up and down and up and down and up and down, I'm going to have local relative or multiple relative mins. Yeah. So we're going to practice identifying them on a graph. First by doing this visually, just looking at the graph, and then I'm going to show you how to do on your calculator. And then we'll take those skills and apply them to absolute extremes. Yeah? Okay. So first example says identify any local extrema in the graph P of t shown on the right. P of t, yeah? So I'm going to separate this into two categories because I know I have two types of extrema. I have maxes. So I'm going to draw all my maximums in red on my graph. And then we have minimums. I'm going to do those in blue on my graph. So we will start with maximums. Those are the tops of hills. On your fingers, show me how many maximums you see in that picture. I see ones and I see twos. Ones and twos, ones and twos. So somebody who said one, why one? Allison and Ziza both very clearly had ones up. Can one of you tell me why we won? The little hill, right? So this little guy? Okay. Those of you who said two, where's the other one? There's three. There's three. Where are the other two maximums? Ah, I am glad that you brought that up. So looking at the whole picture, there are points at the edge of the graph that are higher. Are those end points? Giancarlo is shaking his head no. Allison's shaking her head no. I agree. The reason they're not endpoints is they're not dots, they're arrows. So what these guys represent is a curve that's going to go forever and ever and ever upward, upward, upward. It's never going to stop going up. So it will never max out. So you're right. Those points are higher than our local maximum, which is why this is just a local max and not an absolute max. He's not the highest point in the graph, but he is the highest point in the region around him. Very good point. Yeah. So we're just focused on little hills and valleys. Yes. Do I have a red pen? Oh, it doesn't have to be red, and I do have markers. Yeah. Yeah. That's actually why I put the markers at the table. Yeah. Good. So we agree there's one local maximum. And what point is that local maximum occurring at? Approximately. 3, 1, yeah. X is 3, y is 1. In other words, as a mathematician, I would say this function has a local maximum at x equals 3 at a height of 1. Yeah? The maximum occurs at x equals 3. The maximum value is the output, which is 1. Very good. On your fingers, show me how many local minimums there are. Local mins, local mins. I see peace signs and I see ones. We seem to have some question marks. So take a second and get the ordered pairs in your head, and then I'm going to start calling on people for ordered pairs for where we think those mins are. Yeah, I'm going to give you about 30 seconds. Where are those minimums? Where do we think there are minimums? Yeah. Ooh. Somebody is feeling a little hostile today. Are we having a bad day today? All right. I need volunteers who haven't spoken yet. Give me an ordered pair where we have a local minimum. Cecil first and then Anela. No? So 1, -1. Can I get a thumbs up if you agree with Cecil? I see thumbs up popping around. Very good. So 1, -1. We have a local minimum at 1 at a height of -1. Very good. Anela, did you see a second one? Good. So at x equals 4, we kind of have to guesstimate what the y value is. Good. So we could write 4, p of 4 if we're not sure, because that at least indicates that I know that there's a minimum at x equals 4. Or you can guesstimate. So 4, it's less than 1. It's a little bit bigger than a half. I'm tempted to say 0.6. Just to indicate it's a little bit bigger than the halfway point. Yeah. Yeah, very good. It's not as low as the other guy, but it's still a low point in that region of the graph because both sides of that blue point are going up. That's where the graph bottoms out locally. Good. Good. So it doesn't have to be the highest point in the graph to be a max locally. It doesn't have to be the lowest point to be a local min. Just looking for hills and valleys, any hills and valleys. Those are your locals. Yeah? Good. We're going to do one on our calculator. So if you don't already have your graphing calculator out, please get it out. And we see giggles from people who maybe showed up to pre-calculus without their calculators today. Frowny face. Let me make sure my stat plots is off and I'll let you bother mine. Okay. All right, so our second example says graph the function f of x equals x cubed minus 6x squared minus 15x plus 20 and use your TI-84 calculator to estimate the local extrema of the function. In order to use a calculator to estimate the extrema of a function, I first have to graph it on the calculator. So I'm going to give you about 90 seconds to get that function into the y equals menu and press the graph button. Yeah, I'm going to circulate while you're working. 90 seconds. Get the function in y equals and then press graph. Oh no, somebody forgot their calculator. Go get it. Go. Is your locker relatively close? It's fine. We'll wait for you. Yeah, that's fine. We'll fix it in a minute. Yeah. Because you're right. That's not the only one that's good. If you make an e-haul pass, yeah. Wait, to pull up a variable, you're going to press the xt theta n button. Yeah, good. Candy's got it. Okay. So you're sharing a calculator. No, that's mine. That's yours. I was about to say Peyton better have one because he's in both my math classes. Have you picked up your calculator yet? No. Okay. Since you weren't here the day we checked them out, at some point before, after school or at lunch, you'll need to go to the textbook room and check one out. There are videos of what I'm about to show everybody how to do in class today already in Google Classroom. So you can follow along at home later, and then if you have questions, let me know. And you guys got it? Yes. All right, so most of you who have gotten those graphs have probably noticed that the whole curve doesn't fit in the picture. Frowny face. So you're going to press zoom. And you're going to scroll all the way down until you see zoom fit. Zoom fit. Zoom fit. Zoom fit. And you will press enter on zoom fit and it should take you back to your graphing screen. And it shows a much flatter graph. Yeah, and that's okay. So when you press zoom fit, you get a much better feel for what that graph looks like. And we get kind of like this number and kind of does that, yeah? And that's a rough shape. That's not accurate by any stretch of the imagination. But that's the general idea, yeah? Oh, yours looks a lot flatter in the middle than some others. Yours definitely, yeah, you should definitely have bumps. Yeah. Yeah? You're supposed to have bumps. Double check that you entered your equation correctly. There should be bumps. I definitely wrote this function so you had bumps. Otherwise, there's no point in finding the maxes and mins. Minus 6x minus 15x plus 20. Man. You may. So I can see that there are bumps because I can see it's going up and then down and then up. So that may have to do with what your graph looked like before you hit zoom fit. Let's see. There we go. Yeah, it was you had a non-standard zoom window when you started. Oh. So if that happens, go to zoom. There you go.
Wait, this is right?
That's perfect.
Oh, it looks like there's barely...
So zoom standard. No, that's okay. So zoom standard, and then once that's graphed, go back and do zoom fit. All right, so in order to find maxes and mins on our calculator, we're going to press, I have to look at your calculator now. Thank you. We're going to press second and then trace. Second and trace. Second and trace is the calculate menu. And you will notice it asks you for maxes and mins. So let's start by selecting max. Shh. Can somebody with their calculator in front of them who selected max explain to us verbally what you see on your screen? It sounds like Vicky's got it on her screen because she's verifying and it sounds correct. What do you see on your screen, Vicky? Good. So Vicky's cursor is on the curve and it's blinking and it's asking left bound question mark. And what you need to do is you need to move the cursor to the left until that left boundary is sitting on the left side of where you think your maximum is. Doesn't have to be precise, but you want it to the left of where you think your max is. What the calculator is asking you for is a search area. Where should it look for that local maximum? So we're going to set our left bound by moving the cursor to the left of the peak and pressing enter. After you've done that, what do you see on your screen? You see a line where your left bound was, and now what is it asking for? A right bound. So you're going to move your cursor to the right of where you think your peak is. So once the cursor's to the right of the peak, you're going to press enter. And after you've done that, what does it ask? Guess. And you're going to press enter again to say, yes, please guess. And it should, after you've pressed yes, guess, give you an ordered pair at the bottom of the screen. Can somebody with an ordered pair at the bottom show it to me?
I don't know if I did it right.
So you have a maximum at x is -1, y is 28.
Is that right?
Yeah, -128. Yeah. Bottom of your screen, after you've done that left bound, right bound guess, you should see an x coordinate and a y coordinate at the bottom of your screen. Okay, so you graphed it. So you're going to go zoom. You're going to go all the way down to zoom fit, which is off the screen. There you go. Enter. It's going to give you a weird curve. It's thinking. Very slowly thinking. You see the click wheel of death. There we go. Good. And then in order to find our maxes and mins, we're going to hit second trace. And then we want a maximum. Good. You're going to move your cursor to the left of that little peak there. Well, over further, further, further. It's better to be overly cautious. Good. And then enter to set it. And then move it to the right of where the peak is. And then enter to set it. Oh, stop, stop. We don't want to get to the next valley. There we go. Okay, and then enter. And then enter to guess. Yeah, and you get about negative 128, which is what Candy got. Yeah, good. Is it about negative 1 and 28? So that rounds to 1 and 28. Yeah, perfect. Yeah, no, that's perfect. Some of you on your calculator are not getting exactly negative 1. You're getting negative 1.000001 or negative 0.9999999. And that's okay. Round it to the nearest whole number. What it's showing you is that in the calculator memory, it's doing an estimation procedure for where that highest point is in the region that you set those boundaries for. Candy's calculator did it better. Some of your calculators may be older software. Yeah? So round to the nearest whole number. Good. We're going to get a chance to repeat because I see a minimum in my graph. We get to it the same way. Second trace. And then you select a minimum from the option menu, and it's going to ask you the same 3 questions. Where is my left boundary? Where is my right boundary? Do I want to guess? And the answer is yes. Yes, you do want to guess. I'm going to give you just a minute to do that. I'm going to ask you to share your answer. So 5 and negative 80. 5 and negative 80. I hear it in a couple places. And I heard that pop up around the room, so we're getting like 4.999s and 5.001s and negative 80. Good. Out of curiosity, when you pressed second and trace, what else in that menu looks like it might be useful other than max and min? Intercepts. It can found x and y intercepts. It finds the y-intercepts and it finds the zeros, which are the x-intercepts. Good. And those are going to work very similar to what we just did. The y-intercept it'll zero right in on. The zeros you'll have to provide boundaries, just like we did for maxes and mins. If you were struggling to follow along, there is a video posted in Google Classroom that shows you how to do this. It's under the course resources module at the very top of Google Classroom under the classwork. Yeah? Okay, questions on what local maxes and mins look like? No. Okay, let's take a look at absolutes, bless you, and then we'll be done. All right, so absolutes are what, brain fart, Jesus was thinking for our very first graph, which are the highest points for the whole function or the lowest points for the whole function. So an absolute maximum occurs at the highest point in the domain of the function. And an absolute minimum is the absolutely lowest point in the whole function. Bless you. When we have graphs that have arrows that go on forever and ever, we typically only look at relative maxes and mins because there aren't highest and lowest points. They go into infinity. When we are dealing with finite functions that have endpoints and not arrows, we can talk about absolute maxes and mins. Sometimes absolute and relatives will overlap. Sometimes the top of a local peak will also be the highest point in the whole picture. Sometimes the bottom of a valley will also be the lowest point in the whole picture. So it is possible that your absolutes correspond to relatives. They can be the same point. Yeah? If that point is both, label it as an absolute. So we're going to do some examples. First example, we have a graph of a function here. And I can see that the domain of the function is from -2.5 to +3. Yeah. And it says find all of the local and absolute maxima and minima. So we'll start with maximas. All right, so can people start giving me x values where they see a peak or a highest value? I see 2. I see Ziza nodding. I see 1 at -2 and 1 at +2. Andy is nodding in confirmation. Very good. Those are the tops of peaks. So technically they're local maxes because the points around them are lower. The question is, are those also absolute maxes? And Ziza is nodding. They are the highest points in the whole graph. Those are the biggest y values in the picture. So I would list them not as local, but as absolute. And there are 2 of them at the same height. I have -2, 16 and +2, 16. So that tells me that my absolute maximum of 16 occurs at 2x values, -2, +2. Very good. All right, next question. We're going to start looking for mins. All of the mins in the picture. We'll start with the local mins. Where are the bottoms of valleys? Raise your hand if you see the bottom of a valley. Anila, what do you see? 0, 0. Very good. Not the lowest point in the picture, but the bottom of a valley, everything around it is higher. Very good. Unady, is that my absolute min? No, where's my absolute min? Yeah. The lowest point in the entire graph is that right-hand endpoint. And it occurs at x is 3, y is -10. Yeah. So my absolute min is -10, and it occurs at x is 3. I have a local min where the graph temporarily bottoms out at x equals 0. Very good. So local mins are tops and bottoms of peaks. Absolutes are the absolute highest and lowest points in the whole graph. Yeah? Very good. Very good. All right. I think there's one more example. I'm going to have you guys walk me through it. Yeah. So in your small groups, take a second. Identify local and absolute extrema. I'm going to give you about 90 seconds, and then I'm going to call on some people. Put your phone away. Brownie face. So start by just making dots where you think the tops and bottoms of valleys are. So in this picture, where's the top of a peak? So make a dot. Perfect. Bottom of a valley. Right there. Perfect. And then just identify the coordinates at that point. Good. There you go. Good. You may. Okay. Let's see. We'll start with maximums. Sylvia, where do you see a maximum in that graph? X equals what? -2 and 1. We have a vote for, ooh, I guess I should get my pen going. We have a vote for -2 and 1. Can I get thumbs up if we agree? I see thumbs up popping up around the room. Very good. As a class, we need to decide local or absolute. And I heard local, which is good practice when there are arrows on the edges of our graph, because we don't know what the function does once it exits the graph. These could go presumably back up again. I don't think they do. I suspect the axis is an asymptote, but I don't know for sure. Good. Very good. All right. Next one. Ethan, where's our minimum in this graph? 2, -1. Can I get a thumbs up if you agree? I see thumbs up. Very good. And I'm assuming that is also a local min. So highest point is +1, lowest point is -1. Highest point occurs at x is -2. Lowest point occurs at x is +2. Very good. A word of caution before we move on to our next activity. When you are working in delta math, sometimes delta math is going to ask you for the ordered pair at the maximum minimum. It's going to want both coordinates. Sometimes it's going to ask you where the maximum occurred. So if it asks you where the max is, they're asking for the x coordinate. If they ask you what the maximum is, they're asking for the y coordinate. Because what is the maximum height? That's a y value. Where is it is asking where on the x-axis did that max height occur. So where is an x coordinate? What is a y coordinate? Sometimes it'll ask you for both. What is the coordinate of the extrema? And you'll give them both. Yeah? First step is what we were doing. Draw them on the graph. Yeah? Label them and then pick off those coordinates. Good. Questions on local and absolute maxes and mins? No.